All right, so we're going to talk about average versus instantaneous rate of change today. We're going to really highlight the difference between what you've been doing in algebra up until now, and we're going to add this new derivative aspect into rates of change. That's going to give us what's called the instantaneous rate of change. Right? So, as students of life and of algebra, we studied many rates of change in different scenarios, right? So one of these could be like how fast you drive. A lot of you guys are now juniors and seniors, so you guys are now driving, have driver's license of your own. Maybe. Maybe you're already driving. But how fast you drive is something that is a model, a real-world scenario about rates of change. Think about when you get on a highway, you have to accelerate, you have to travel a certain velocity on the highway. You can't exceed a certain velocity or you may encounter the police who may give you a ticket. At your own risk, right? Yeah, how our savings grow over time. So a lot of parents may be talking about like their 401k or maybe they're saving for their college fund or something like that. Savings can grow over time in certain accounts in finance. You have like a money market account, you have like a CE account, etc. So you can earn money over time. The rate at which the world population changes. So I don't know if you guys know this, but the rate at which the population grows is exponential. So that's grown at a specific rate. People over time. So the number of people over months, years, days, whatever you want to do in terms of like a time unit, but that's a rate. Your growth rate, you guys are teenagers, you're growing faster than ever. Imagine you freshman year compared to now some of you guys senior year. Have you grown since then? Yes. Yeah. Eventually you curve off, it's like, then you just grow this way instead of that way. Right? Grow this way. But yeah, growth rate changes every year. Unemployment rates, okay, those change. Those have fortunately been going down since the crash in 2008. But still a rate that's ever changing, correct? So what do we use to kind of like analyze these rates which we encounter every day in our lives? Well, in each of these studies, we can express one variable in terms of another. All right, and in mathematics, we talk about that being y as a function of f of x, right? So y equals f of x, y as a function of x. So we're actually going to talk a little bit about these functions, how their rates change over time. But I just want to give you kind of some things about can change occur at an instant. One of the scenarios and examples I'm going to use today is pretend you're driving your car and someone takes a picture of your car. A picture is a moment in time. It's a split second, right? And time is frozen. And ask yourself, okay, if I was driving a car and someone took a picture of me 15 minutes on my 20-minute drive, how fast were you going at 15 minutes? Can we determine how fast you were going at the 15-minute mark? What about the 15-minute mark in 1 second, 15-minute mark in 2 seconds? Can it change? Can we analyze that? And the answer today is going to be yes, and calculus helps us do that. All right, so we have been talking about this idea of average rate of change for a very long time. You guys are probably almost tired of me talking about it at this point. But just to drive home the fact here is that an average rate of change is defined by the total distance you travel over the elapsed time period. We call average rate of change like the slope. But that is almost sometimes not a good representation of the rate of change that we're looking at. So for instance, I think the first day of school I used Evan as an example, his drive to Chick-fil-A. Sometimes he's going to be driving faster because he doesn't have anybody in front of him. But if he's leaving directly at school at 3:20 and he's trying to get onto Nevin Rogers Road, is he traveling very quickly? No, it's going to be probably a standstill. So sometimes he's traveling faster, sometimes he's traveling slower. But most of us would measure his average rate of change being the total distance he traveled, the amount of, the number of miles between here and Chick-fil-A. I think we said it was like around 7. And then the time it took him to get there. And then we would divide those, and that would be his average rate. So he averaged this many miles per minute, or this many miles per hour if you chose to use that time thing. That's what average speed is, okay, in terms of like an average rate of change. Remember graphically, if you guys want to do this, we're talking about that being a secant line. So if you have 2 points, you're going from point 1 to point 2, and you're going to measure the rate of change there. You guys know this is slope. How much did you go up and how much did you go over? But this is nothing new that we have been studying. This is something that's been a trend in your math education for a long time. You extensively studied this average rate of change in Math 1. We talked about it at the beginning. We did our calculus review. And now we're kind of going to compare this average rate of change to an instant rate of change. Back when we talk about developing the idea of the tangent line problem, if we wanted to come up with a tangent line to a point, remember that we have to use this blue secant line, correct? And we have to use what idea that we studied in Unit 2 paired with that. Talk about the idea of a limit, remember? And you're trying to move this point closer and closer and closer to that one point to find the tangent line, because there's a difference between a tangent line and a secant line, correct? On the next page, which we'll get to in a second, but just make sure that you guys know here that average velocity is going to be your change in position over your change in time. All right? So it's the change in position over the change in time. That is what your average velocity is. You're going to see some textbooks talk about this S function. Do you guys see it says change in over change in t? You'll see a lot of textbooks talk about distance being with the variable s. You could also just write it as change in d, so the triangle symbol d over triangle symbol t. So they're kind of synonymous, kind of like when we call the derivative y prime, f prime x, dy dx, d dx of the function, all being the same thing, same idea here for distance, right? All right, we're ready to move? All right. Instantaneous rate of change. Now, this is going to be a little different. You guys can see the difference between the two graphs that we are going to analyze. But the instantaneous speed, or the instantaneous rate of change, is a speed at a specific instant in time. So you're interested only at one time period, not between two. Not from start to finish, but at like I guess I was giving an example, the 15th minute or the 2nd minute. You care about a specific moment in time, right? And that's going to be the limit of the average rates of change. So that's going to be this idea of taking and finding how fast that curve is changing at a point. Okay, and that's the idea of a tangent line. The rate of change at one point. That's the whole idea behind the derivative. Okay, remember, how many points do you need in order to write the equation of a line? How many points do you need to write the equation of a line? 2. How many do you have here? 1. But now using this idea of a derivative, and as the limit of the difference between those 2 points gets very, very, very small, we can basically write the equation of a line given 1 point, as long as we know something about the function, like its equation. We can take derivatives. We have techniques for doing that. And remember, the rest of the week after we do this, we're going to be learning these different algebraic techniques. And if we can't do it algebraically, I'm going to give you another method that you can do. Right? So graphically, it's going to be the speed of the slope of the tangent line at a specific point. All right? Basically, what does this sound like? The instantaneous rate of change. It's the instantaneous speed is the slope of the tangent line at a specific point. That sounds just like what we've been talking about, which is a derivative. So when you think of the words instantaneous rate of change, you're thinking of basically the derivative. All right? So that's why we use derivatives in calculus, because it gives us the speed of something traveling at a moment. Oh, sorry. And that's why this is cool in calculus. That's like why we're going to study this for a couple months. Because this whole idea is really, really interesting. Now, I want you to think about if C moves to be here. is the speed at which that curve is changing different from the blue tangent line if I drew that red point? So basically my question is the speed of the curve changing from the blue point to the red point? Yes, because what would I need to do to measure the speed of the curve at this red point? Tangent line there, right? Yeah, see that? What's the difference between those slopes? Do you know them? Like numerically? No, but what happened? It went from positive to what? Negative, which means something is going from speeding up to what? That's the ideal. You guys see what I'm saying? Okay, so that's why this is going to be kind of interesting. All right, velocity. Now, we just talked about average velocity is the change in position over the change in time, correct? But instantaneous velocity is ds dt. All right, it's a derivative of the position with respect to time. All right. So we're going to call that s prime of t. So basically, you're going to have a position or a distance, and you're going to take the derivative of that, and that's going to give you velocity. So here, when you see that says velocity is the blank of position, velocity is basically the derivative of position. You have a function that measures distance or position. You take its derivative. That new function that you come up with is the speed, the velocity. All right? And we're going to do some examples of that. That's good? All right, let's do some examples. Now, these examples are not going to be super complicated. Like, you guys know how to find average rate of change. Before you walked in today, you knew how to find slope of a line. Knocking on wood, right? Yes? All right. You guys see our first example? Roller coasters. If we ever can go on a field trip in calculus, guess where I'm going to take you? Carowinds. Because that is literally the place of calculus. It's like the shrine of calculus. Because you have roller coasters, and roller coasters are doing what? It's changing speeds all the time, right? You know how like when you go up on like a roller coaster? How many of you guys been to Carowinds? Okay, most of you. Okay. You're going up a roller coaster, and it's like you're going up, and you're traveling like super, super slow, and it's like to build like this anxiety that you have. You're like, oh my gosh, what am I doing? Why am I on this ride? Did I ever tell you the story about when I tricked Miss O'Neill to get on the roller coaster? That's the funniest story ever. Oh my gosh. I was trying to get her to go on a ride, like on a roller coaster, and she goes, I don't like big roller coasters. I can't handle scary roller coasters. So I convinced her that the Top Gun one in Charlotte, it's like, it's fine. It's like one of those baby roller coasters. You'll be okay. And then she goes, okay, I trust you. And I was like, yes. So literally, we walk in line, we get in there. You know how they put like a harness on you and they lock you in? And she goes, are you sure this is one of those not scary roller coasters? And I go, I lied. It is. Have fun. And she goes, I'm going to kill you. But she didn't actually kill me. It's all right. But anyways, so let's think about a hyper roller coaster, correct? Hyper roller coaster. That's a special circuit roller coaster with a height measuring greater than 200 feet. So if you have a new roller coaster which is under design, it has to have the large drop on the circuit modeled by this equation, which is d of t. D of t is going to be measured in feet, and time is going to be t measured in seconds. Okay, so you have some function. All right, you're relating time to distance. Does that make sense? All right. So this is basically what it looks like. I wanted to make sure you had the visual. You guys see that visual right there? Funny story, as I was Googling pictures about hyper roller coasters, I came up with this picture. And it made me laugh because I was like, what the heck is this? This is like an ebus. This is like a random bird. And this was like all over like the images. Literally, this woman was riding a roller coaster and this bird like hit her in the face. As she was doing it. Like the 4 or 5 pictures in a row, I was like, why is this? Is this like a news story or something? Apparently, it was like a bird that flew into her when she was riding a roller coaster, right? So, there you go. I hope she was going pretty fast. I mean, remember, this is a moment in time. So today, what we're going to do with calculus is saying, how fast Was this woman traveling on the roller coaster when she hit her bird? Right? Like, how? What did you say?
They actually hit her?
No, we literally did. I watched the video. Oh, you can Google it. Just Google like woman hit by bird on roller coaster. I know, the random things that the only thing I wanted was hyper. I just typed in hyper roller coaster so I could give you guys a visual, and then this picture popped up like 7 times. Literally, there's a video that goes with it. It's super funny. Okay, but if we have time at the end, I'll show you. But anyways, so our big calculus question is, how fast was she traveling the moment she got hit by the bird? Can we do that? Can we measure that? And the answer is yes. And guess what? You have the skills to do it. Let's get started. All right, so here we have d of t, correct? That is a position function. It is measured in feet. You guys with me? Notice that I graphed it here for you. You guys see the graph here? You don't have this graph, but I have this graph. All right? Notice that it's a cubic function. You guys see it's a cubic? Back from Math 3, pre-calculus, cubic functions are kind of like this S-shaped graphs. It's a little wider. Based on how it's been moving, right? But it's a position function. It measures feet. If you input what? If you input this, it gives you feet. Time, measured in what? Seconds. Seconds. So here, can we find the average speed of the hyper roller coaster from 2 seconds to 6 seconds? Yes. Basically, what is that doing? We're going from point here, which is 2, to where? 6, and we're saying, okay, what's the average rate of change over that time span? You with me? So what would we use? Would we use a secant line, a tangent line? What would we do? A secant line. Looks something like that, right? Now notice that the function, as it changes, is not really following that secant line. Sometimes it's traveling a little slower. Do you guys see that? But on average, that's the change. So how could I find this? So when I'm asking you for average speed, what am I basically asking you to find? The slope. What's the slope?
D of 6 minus D of 2.
That's D of 6 minus D of 2 over what? 6 minus 2. So you're going to have to use your calculators, by the way. Unless you guys can cube 6 times it by 1.87. Subtract that from 20.64 times 6 squared, and then add that to 112.79 times 6, and then add 132.56 to that. I mean, if you know that in your head, great, I'm impressed. But then you have to do it again for 2, so it might take you a little while if you're doing that by hand. I should have told you you needed a calculator today, right?
Sorry.
Chase, I apologize. That face, you seem so disappointed. I know. I feel terrible.
Does this mean I make sense to calculator?
No. This example is calculator accurate, though. I'll teach you some cool stuff on the calculator when you're ready, but you're not ready. I promise. All right, so let's quickly do that. We got some other stuff we got to do today too. Besides talk about how people got hit by birds on roller coasters. Say what?
First one is 470.18.
470.18. I agree. 470.18. We can do the bottom one. 4.
The second one is 290.54.
290.54. All right. From there, which simplifies to 44.91. Is that what you guys got? Now, what is this unit now? That's important because you got to understand what this is.
Feet per second.
So this is a what? A rate, a speed. It's distance over what? Time, which gives you a velocity. You guys understand that this is a speed, a velocity? Yeah. Feet per second. So it's important to know what units you're in, right? Everyone knows how to do that, right? Okay, let's get to the goods. What if I asked you instead, what is the instantaneous speed of the roller coaster at 3 seconds? So imagine this poor woman at 3 seconds on a roller coaster ride, bam, bird in the face, right? We'll call it the bird point. Okay. The bird point. So there's the bird point, right? How fast was she going on that roller coaster at 3 seconds? Remember, we only want 3 seconds. Do we want 3 seconds and 4 seconds? No, we are interested in this speed. You guys see that? The moment it hits 3 seconds. So what are we going to have to do? We're going to have to find 2 points, right? Bringing them so close together that basically 2 points become 1 point, which is basically us doing a derivative of this function, right?
Yeah.
So we need to find d prime of t. Good thing we used all those cool rules yesterday, right?
Yeah.
All right, so we can power rule the crap out of this, hopefully. Yeah? Let's do it. So d prime of t. So what's 3 times 1.87?
5.61.
5.61 t what? Squared minus 41.28 t plus 112.79. Done? You guys see that? I use the power rule. All right, now I have the derivative. What do you do now? You plug in 3. Ladies and gentlemen, that's how you're going to get the moment at 3 seconds, how fast that roller coaster is going. You take the derivative, you plug in 3. That's how fast you were going at 3 seconds.
It's 39.44.
39.46. I got 39.44 as well. Thank you, Colin.
Oh.
All right.
Yeah.
So this speed right here at 3 seconds is 39.44 feet per second, which will be different from the speed at 3.2 seconds, which will be different from the speed at 3.7 or 4.9 or 5.7 or 6.0.
But they can be the same.
They could be, but they should all be different because if you're traveling, sometimes you're going to be speeding up, speeding down. It is possible to be the same exact speed. I'm not saying that you can't, because you could be like traveling, for instance, on a curve. So like you could go like this, and then you could maybe level off and then go up and then go back down. And think about this on a car. What could this represent if you're traveling at a constant speed? Cruise control. The speed is constant because you told your car, I don't want to deviate from that set speed. See what I'm saying? But then maybe you need to pass a really slow car, and then maybe you're getting off on the interstate. You see how your curve is changing over time based off what you're doing. This is super cool, guys. Like, this is really interesting. I hope you find it kind of cool. All right. Now, notice that that is our derivative. We call this derivative the velocity function. That's the velocity function because it measures speed. So when you take the derivative of position, you get velocity. Now, what is the meaning of the instantaneous speed in context at t equals 5 seconds? So we have the derivative, right? Do we know how fast we're traveling at 5 seconds? No, we don't, but we can figure it out. What are we going to do? Plug what in? Be more specific.
5 into each times ct.
Into the velocity function, aka the derivative of position. So plug in 5 here, and what should you get? 46.64. 46.64. Excuse me, not 4. Now, Alex, with that, I need units. What'd you say? Feet per second. Yep. What does this mean? Took a derivative, great. You plugged in a number, fantastic. You know it should be feet over seconds, but what does it actually mean? How fast you are what? It's the speed of what? Of the roller coaster specifically, right? So you have to use some context here. Well, what is it doing? The velocity. It's increasing. You guys see that? Why is it increasing? Because the speed is positive. So the speed of a roller coaster is increasing by 46.64 feet per second at when? This is at one moment in time, and you have to specify that moment. When is it this speed and it's increasing? At t equals what? 5 seconds. You have to put that.
By increasing, you mean like increase from 0?
Like it's positive, so it's increasing. Try. Is the word trapping increasing body? How about with this? Yeah. Better?
Yes.
Okay, let's do that. Did you write in pencil? You can erase it. We'll be all right. You'll survive. You guys good? Now, I want you to look at the next example. Notice what you're given in the second example there.
A table.
A table. Do you guys see that? Oftentimes on the AP exam, you're going to be asked to estimate, especially on the calculator portions of the test, what the velocity would be at a moment given a table. So they may not give you a complicated function like I gave you, correct? So what they give you this table. So here it says use the following table of values for the number V of T of gallons of water, thousands per hour, H, that are flowing into a retention pond T hours after a severe thunderstorm. So what are you talking about here? We have gallons of water that are flowing in per what? Per hour. So here, what is V of T here? What's the number of gallons? In thousands, right? So we'd have to multiply our answer times 1,000 if we wanted the actual gallons now, right? So can we estimate V prime of 2? Do you guys understand what V prime of 2 represents? It's the slope of the tangent line at 2, but you have to use a chart. Okay, now one misconception is, can I use 2? And the answer is no. All right, because you don't have the derivative, like you can't take the derivative of a function. All right, but you can use the surrounding points to kind of estimate what it should be. So what's going to be kind of close to 2? So I could find the change here between those two, right? So basically, what are you using to estimate the slope of that tangent line? You're using 2 points, right? So you're estimating using 2 points. So here, V prime of 2 is not exactly, but is approximately going to be equal to the average rate of change between these 2 points. So I need to say, what is V of 2.5 minus V of 1.5 divided by 2.5 minus 1.5? Because that's the moment it leads to, but we don't have any function with each have a table of that.
We just have to, this thing about the equivalent.
Yeah, well, I guess you could say it like that. I guess you could use 1.5 and 2, and then 2 and 2.5, but I'm just going to use 1.5 and 2.5. Oftentimes, when they give you a table, you're not going to actually know the value you're talking about. When we do the next question, you're going to see what I'm talking about. All right, so from the table, that's going to be 1.24 minus 0.93 all over 1. Is that correct? Just using the table. What is that going to give you here? You actually need to be able to do this without a calculator. It is 0.31. Now, we can't just say 0.31 and we're done. That gives you kind of half of it, right? What does it mean here? 0.31. you guys understand that this is a rate, correct? After 2 hours, right? So this means after 2 hours, that's your time, related to the position, I guess the number of gallons, quote unquote, right? There is about what? How many gallons does 0.31 represent? If the gallons and that decimal are in thousands, like you have to represent it in thousands. So you have to do what? Times that by 1,000, right? What's 0.31 times 1,000? 310. So there's about 310 gallons of what? Water doing what? Flowing into a retention pond. You guys see? That is basically, we're discussing a rate.
It's really low flow.
Well, do you want it to be here?
Can I have fast flow if there was such a point?
Yeah.
No.
Okay. I didn't know if you wanted that or not. It is meant to be that, like a place for water to go. I'd want to go there, right?
Yeah.
But it depends on if you wanted to go there or not. So I think that's important. All right, what about next one? When does the rain flow or rainwater flow begin to slow down? Question mark. Estimate the instantaneous rate of change at this time. So take a look at the table. When does that number of gallons start to decrease? Do you guys see that it's increasing to start with? And then what does it stop? Sometime between what? You know if it's going to be starting to stop or starting to slow down closer to 3 or closer to 2.5? You don't know. But it's happening somewhere in that time frame, correct? So when does it start slowing down? All right, well, you know that it's going to start slowing down when V prime of, V of 2.5. So V of 2.5, once that we know that was greater than V of 3, that's going to be the time. So we know it's going to be sometime between 2.5 and 3 seconds. Seconds? Hours. Hours. Sorry, you have to keep my in units. They're all different. All right, so how do we estimate the instantaneous rate of change at this time? So we need V prime of, I'm going to say V prime of between 2.5 and 3 because we don't know that time, right? But we're approximating what it is. All right, calculate my slope. What's my slope going to be? V of 3 minus V of 2.5 all over what? 3 minus 2.5? Yep. All right, calculate that real fast. I'll put the numbers in for you. What's that going to be? 10 or 1.05 minus 1.24 over 0.5. All right. Okay. So what's that going to be? Negative 3.8? No. 0.38. Oops. I miswrote it on my paper there. What does that mean?
So 380 less than
It's about negative 380 gallons per hour. It's a rate. Remember, you're finding a rate. You guys understand that the instantaneous rate of change is like steep. It should be a distance over time when you report it. Okay? You guys okay? Cool. Okay. Why not? All right, flip it over because I want to show you a problem. So where are you going to see these kind of charts? So here's your AP Calculus first free response, at least the partial portion of it. This is what it looks like. When was this from? 2018. Is that pretty recent? Absolutely. Take a look at it with me. The height of a tree at time t is given by a twice differentiable function. Spoiler alert. Twice differentiable. How many derivatives are you going to take? 2. That means it can be derived twice. You mean we have to do a derivative and then a derivative again? Yes, you can do that. All right? So that's what that means. Where h of t is measured in what? Meters, and t is measured in years. Selected values of h of t are given in the table above. You guys see that? So I got years and what? Meters. So this is a time, that is a distance. What is it asking you to do here? Use the table to do what? Estimate h prime of 6. Then what does it want you to do? Incorrect units, interpret what? What does it mean? You can do this piece on the problem. Out of 9 points on every free response you can earn, this one was 2 points. You get a 2 out of 9 if you can do slope and interpret. Yay! That should make you feel good. You only need to average 5 points to make a 4 per free response. You average 6 points, you're making a 5. 2 of the points on this one were what? Can you do slope? You want to try it?
No.
Do it. You can do it. We just did one just like it. See if you can do it. I'll give you a couple minutes. Find h prime of 6 and interpret it with using correct units. Shoot. All right, I'll put my answer up here when you are ready to check. You would get 1 point for this and 1 point for that.
That's not like how much it is growth. Like
I would ask you to interpret what it is in the context of the problem. It's the rate that you're growing at 6 years. You can also say rate that it's changing if you don't want to do that growing. How do you feel about doing this? Okay. On your test for derivatives, guess what you're going to have as one of the free responses? A made-up problem just like this, where I'm going to ask you to make sure that you know how to calculate it, and estimate from a table, and then interpret. Yeah. There was a subsequent parts to this free response. This was only part A. No, there's no free response that's just only on like this. The free responses are literally blended together. So that's the only big difference between this and if you took stats with me, we know we started like week 1, I was throwing AP free responses at you because they're segmented by like chapter and unit. These are interwoven. Like there's no like I can give you one and you know how to do it yet. All right, guys good? All right, next conversation we need to have is about acceleration. Okay, acceleration. So So we've talked about what two things so far? We talked about position and talked about velocity. The last thing we're going to talk about is acceleration. Now, the average acceleration, very similar to the average velocity, is going to be the change in velocity over the change in time. Right? So instead of the change in position over change in time, the acceleration is the change in velocity over the change in time. So average acceleration is going to be the change in velocity over the change in time. So you can think of that as delta V over delta T. But what if I'm interested in the instantaneous acceleration? Not the average change in acceleration, the instantaneous acceleration at a point. Well, that's going to look like dv dt. And dv dt is me taking the derivative of the velocity function. If you recall earlier, if I took the derivative of velocity, that's going to give me now acceleration, but I already took the derivative to get velocity, right? From what function? Good, the position function. Good, yes. That's right, you guys are all comatose after eating lunch. All right, so the acceleration is now, what we're going to say is the derivative of velocity. So today you will take your first double derivative. I will give you a position function. You take its derivative, you get velocity. You take its derivative, you get acceleration. All right? So the double derivative of the position function is the acceleration function. All right. So you guys probably see that below, right? You guys see the little acronym there? PVA? PVA. What do you think P stands for? Take its derivative, you get velocity. Take its derivative, you get acceleration. That's how it goes. Position, velocity, acceleration. So what do we represent S of t to be? This is position. This is the position function. This is measured in some sort of distance like feet or meters. I take its derivative. Its derivative is a rate. That rate is called velocity. How do we measure that? Feet per second, meters per hour, etc. Do you guys understand I'm just making up these units? Yeah. They could be, miles per day, millimeters per millisecond.
Is this meters per hair? Oh, hours.
Meters per hair, yes. Meters per hair.
Double
derivative of position is the single derivative of velocity, and both of those things are the acceleration. Now, what are the units for acceleration?
Oh, meters per second squared.
So if I have feet per second, the time unit is now squared. So it'd be meters per what? Hour squared, etc. Right? So acceleration, you have distance over time squared. You do it again, you'll get distance over time cubed. If you even want to. I don't know why.
What would that give like?
Oh, I don't know.
So
we can investigate that. Google is a thing for that reason.
All
right, you guys good? Have that copy down? Iona, you're going diving, my friend. Iona is going diving. Now, Iona is diving from a board 32 feet above the water with an initial velocity of 16 feet per second. Her height is modeled by the function S of t equals that quadratic expression. All right? Now, does anyone know what that negative 16 represents?
Is it like gravity?
It's gravity. It's acceleration due to gravity. Okay? But since this is measured in feet and not meters, that's why it's not negative 4.9, whatever. I know gravity is negative 9.8 meters per second squared or whatever, but you divide it by 2 when you use this general free fall function. Anyways, what is S of t? It's position. This is measured in what? Feet. No, not meters. Well, unless it says meters. No, it's just feet. That's feet. You guys see that? All right, let's answer the questions. Answer the questions with me. When does Iona hit the water? What would the position, or what position, like, would you be at when you hit the water? What is 0? The S of t, right? So when she hits the water, S of t is going to be equal to 0. I mean, you could draw like a little diagram, right? So here's Iona. Oh, hold on. You said blue, right? Blue hair. It's just going to go diving, right? So.
That will pick. What do you put it up? Low power.
Whatever. Don't judge. Okay. But anyways, this is when S of t is equal to 0, right? S of t is equal to 0. She has, you know what? She has like a force field that's doing this, okay?
Like Hilbert today.
Okay.
Air resistance does not exist on this planet.
That's true. We ignore that a lot here. Okay. So we're going to set 0 equal to 16t squared plus 16t plus 32. Okay. So when her position equals 0, she's hitting the water. Agreed? All right. Now, this goes back to Math 1, Math 2, Math 3, sure. Can you solve this quadratic? Great. You guys see the GCF of negative 16? So it's going to be t squared plus, or minus, excuse me, t minus 2, is that right? So that's negative 16. Then what's this factor into quickly? T minus 2, t plus 1. You guys agree?
Yep.
So then the time is either going to be t equals 2 or t equals negative 1. Iona, are you a time traveler?
Yes.
No, you're not, because time travel doesn't exist. The Vulcans proved it false. All right. Let's start. That's what they say. But they were obviously wrong, which is okay. So time equals 2 seconds. Seconds? Seconds is when Iona hits the water. You guys good? We can understand that.
We would not just.
Now, next, look at part B. How fast was Iona going when she hit the water? I want to know how fast she was traveling when she hit the water. So what am I interested in? Am I interested in position?
No.
What am I interested in?
Velocity.
So I want v of t. Now, v of t, my friends, is just the derivative of the position. So quickly use your power rule techniques. Boom, boom, boom. And you're going to get negative 32t plus 16. You see that?
You're screwed. Get back to the last one. It says that 32 feet above the water with the velocity of 16. Could you just divide the v by the velocity and then you also get 2 seconds?
Sure. Next, how am I going to find out how fast she's traveling at 2 seconds? Plug in t for 2, right? So do you guys see that it takes her 2 seconds to hit the water? I want to know how fast velocity to do that. So now this is going to be v of 2 is equal to this. So how fast was Iona traveling when she impacted the water? Negative 48 miles per hour. Iona, you must have like a
She's got that force field.
that big force field of a skull, because you're going that fast. I don't know about that skull, but there's a force field, so it's okay, right? So this would be feet per what? Feet per second. You guys see why it's negative?
Yeah.
Because she's traveling which way? Downward, right?
So Iona has superpowers.
She does.
That's
What's Iona's acceleration? Take the derivative of the derivative you just found. So v of t, you told me was negative 32t plus 16, correct? What's the v prime of t? Negative 32. In general, done. Use units. Feet per second what? Squared. Good? Cool? Happy? Next. Put it all together. Okay, so this is what we call the general free fall function. It gives position based off time. So you're going to see this s of t equals negative 16t squared plus v sub 0t plus s sub 0. You guys see that? Now, do you guys see that this v sub 0 is the what we call the initial velocity? So it's the initial velocity. So it'll tell you what the initial velocity is. S sub 0 is going to be the initial height. So where you start the height, correct? So where you start the height. Okay. So Henry, you dropped a watermelon off a building. I'm not sure why, but you do. It's you, so I'm not surprised. It was a 2,000-foot tall building. This is what you were doing some calculus homework, right? With an initial velocity of 0 feet per second. So can we write each of the three equations here? Position, acceleration, velocity. Can we write the three ones? Let's go. S of t. Negative 16t squared plus 2,000. How fast was the watermelon going when Henry decided to drop it off a building? Negative 32t. And its acceleration? Negative 32. And we know that's going to be in feet per second, right? Squared. So maybe there's a parallel between the watermelon and Iona. Maybe the watermelon was Iona. Maybe Henry pushed Iona off the building. Whoa. How about this? We're going to do watermelon. There's a watermelon for Iona. That's all right. We'll get Viola Davis on the case. She will not let you go unavenged. All right. Are you guys good with the three functions there? No? Okay. But do you understand where they came from? Yeah. More or less. Okay.
A certain amount.
Read number 2. What does number 2 say? Determine the average velocity. What is it asking for? The average velocity. If I want to know the average velocity, the average velocity. I want the slope. AROC. Yes, AROC? Okay, cool. Okay, just making sure. So which function am I using? Position, velocity, or acceleration to find average velocity? Position. This should be s of 3 minus s of 1 all over 3 minus 1. So if you're trying to find average velocity, you take the position and divide it by time. When do you use the velocity function? When it says instantaneous rate of change. At an instant, you use the velocity function. If it's average rate of change, you use position, you divide it by time. All right, so what do we get here? This should be 1744 minus 1936 is what I have, over 2. Can someone check me there? 1744, 1936.
What hasn't been previous?
Yeah, how am I doing? Did I not get those right?
says for 3 weeks, 8 and 6.
Oh, yeah, but it was also.
Can someone check me?
I got
You did?
Well, yeah, that's still happening.
We can change it.
Continues to.
I just need someone to verify that I was wrong.
I got
1856? Okay, let's do that. Sorry. All right, so what is this going to be?
I got 1984.
Okay.
Yeah.
I must have typed in something wrong. I apologize. Okay, are those two right now?
Yeah.
All right, so now you guys do it for me because I have it.
I just, we have negative.
It said backwards.
That's the right way.
That's the right way.
That's the right way.
So when you're-
It's negative.
So it's negative.
you said what happened.
What did you say, 16?
4.
4? What is it going to be? Landon, Cullen. This is why you're behind and Ryan. You're talking to him.
Behind what?
Well, he is. You're not. I don't know if you're right back there. I'm talking to Landon.
I'm just gonna I'm just loving these guys.
All right, we already found the velocity function, right? We want to know the instantaneous velocity. What are we going to do? Plug in 1.5 for v, correct? So that's negative 32 times 1.5. Negative 48. And what's the units? Regardless if it's average velocity or instantaneous, the rates are still the same. It's going to be position over time. So in this case, feet per second. Goes with me? That one's easy. All right, 4. Find the time required for the watermelon to hit the ground. The watermelon hit the ground. So what would the position need to be if the watermelon's hitting the ground? 0 is that equal to negative 16 t squared plus what? All right. Now, we don't have much more time together. But I want you kind of just to, you can go from there, I hope, right? You can go from there. Solve that quadratic. Subtract 2,000 divided by 16, take square root. Okay. Then you're going to use that time, and you're going to plug this time into v of t, correct? And then I want you guys to look at number 6. You guys see, what is the velocity when the watermelon has fallen 1,000 feet? What would you need to do to 1,000? If it's fallen 1,000 feet, how far has it moved? 1,000 feet, right? So what are you going to put that in for?
S of T.
S of t. So this one would be 1,000 is equal to negative 16 t squared plus 2,000. So you guys see that? When it falls that far, that's what you're going to do. Okay. All right, please make sure you jot down your homework. You can also find it on my website. But I hope you enjoyed average rate of change and instantaneous rate of change.